and maybe the rest of the world too. All right, so in terms of the skill though, find the distance between 0, 3, 6 and the line with parametric equations given. So PM is the displacement vector between a point on a line and a point in space. All right, so we have the distance between point 036 and the line with those parametric equations. So the assumption here is that we're referring to point M with those coordinates. All right. Now point P, we're going to pull that. So we're going the other way here. We're pulling it from the parametric equations. So what I can do is I can get my displacement vector for the parallel vector. That's just going to be the set of coefficients for the variable t. So -1, 2, and 3. But the point P itself, that point P living on the line, that's just going to be, we're going to call that point P. That's really the PO that makes up the line itself. Because we could have chosen any point on the line. I just choose to use the one that's staring me right in the face. All right, so 1, 1, 5. All right, so that's all sorts of information that we have. If I want to come up with PM, that's not too bad because I have my P and I have the M. I'll rewrite it down here. If I want PM, all right, the M coordinates subtract the P coordinates. So -1, 2, 1. All right. So actually, it's not too far off from the displacement vector associated with the parallel vector. All right, so that's pretty not bad. All right, so what I need is the cross of that and vector V. All right, so that vector V is like, where does vector V come from? Well, vector V is the vector associated with the line itself. All right, so the line has vector V. Well, we call that P0, P1. So that's my vector V. So in effect, I just need the cross product between these two vectors. All right, that'll give me my numerator. And then I just need the magnitude of the vector V to begin with, and or to end with, I guess. I mean, sometimes I don't even know what I'm saying. But but that would be it. It's the quotient of those two things and we'll have it. All right, so I'm just going to shunt this down a little bit because I can tuck in the magnitude. I'll just kind of throw it in right here. So the square root (1 + 4 + 9), the square in each component. So we're looking at root 14. That root 14, that's come up a few times already. So, like, I'm not saying you can rely on that always being the magnitude of a vector, but it comes up pretty frequently. Okay? So I know what my denominator is going to be. Now it's a matter of coming up with the numerator. So I want the magnitude of the cross product. All right. So just a refresher. So because we have other techniques that we could use, we could find the cross product and then find the magnitude of that cross product, or we can use one of those handy dandy formulas. Let's see if I remember where I put it. Oh, it would be in the cross product section. The magnitude of the cross product, we had that U cross X is equal to the product of those, multiplied by the sine of theta. You could do that, right? But then somewhere along the lines, I jotted down my handy dandy brand new formula, which is where you take the magnitude of each of the vectors that make up the cross. Right, those magnitudes squared and multiplied, subtracting from that the dot product. Right, so just like you got options is really what I'm getting at. All right. The one thing that I'm going to need you to do is I'm going to need you to show work when it comes to this, because you probably know this, maybe more than I do, but like the internet has like websites you can go to that does math for you. All right. Yeah, I'm being a wise ass right now, but yeah, like that's really the issue. So if you just give me a cross product, if I say find the cross product or the magnitude of the cross product, and you just give me the answer without any supporting work, like I don't know. You could be the nicest person in the world, but you got to kind of understand what I see on a daily basis when I'm teaching this class. All right. So, and just to give you a little bit of perspective, this is what I see. I'm going to send it out on Remind. Make sure there's nothing personal up there. No, just my name, which is fine. I can live with that. It's a matter of public record. I'm just going to pop it in there. Next, a photo. All right, so that's what I see if you're looking on Remind. That's what my class is, or my experience with class is. All right, I minimize the faces because I can't take the chance of creating a video that has any issues with privacy. So I minimize the faces, and so basically I'm talking to a screen for 2 hours twice a week just for this class. Right. And so I got to say, there have been moments where I'm like, oh boy, did I forget to like turn on Zoom? Like I literally could be talking to a screen that contains nobody on the other end. Right. So why am I saying it? I don't know yet. There's no reason how I should know yet, I guess. So the only things that I have to go by are the quality of your work, and the detail associated with that work. So it's like, you may be the nicest or the most trustworthy person in the world. I don't have any, I'll say evidence of that on my end, but that sounds too harsh. I don't have any information that allows me to make that judgment. Right. So you got to show me something. Just don't give me the answer unless it's multiple choice, different story. But, you got to show me something. So if you're going with the cross product technique that I came up with and just give me the formula, show some substitutions, then you can go to the answer after that. All bets are off. I don't need you to show me how you like multiply two numbers, but you got to show me something. All right. And I don't want it to come across as people haven't been doing that. It's just I can't take the chance, especially as the material gets more challenging. I can't take the chance that there's going to be any miscommunications when it comes to this sort of thing. All right. So I need the magnitude of PM squared, the magnitude of V squared, and then from that we subtract the cross product of PM. And I'm sorry, dot product. Ooh, geez, of PM and V squared. All right, so I have the V, I need the PM, all right, the magnitude of PM. I'm just creating some room here. The magnitude of PM square root 1 plus 4 plus 1 is going to be the root of 6. All right. Now the dotting of PM and V, that's easier. All right. So I can even chuck that here. PM dot V. And I'll move it all up in a second. I'll reorganize. So is equal to 1 plus 4 plus 3. That's going to be 8. All right. So again, let me just clean it up a smidge, resize it so it fits nicely, or as nicely as I'm capable of making it fit. All right. So I got my dotting, I got all that stuff. All right. So the PM squared, well, that's really just taking the radical and dropping the radical, right? So we're looking at 6 multiplied by 14. Subtracting from that, looks like I lost it. Oh, an 8. 8 squared. All right, so 6 times 14, talking about, looks like 84. 6 times 10 is 60, plus 24 is 84. Yeah, 84 minus 64, and we're looking at root 20. All right, we're looking for a distance that's a linear distance. All right, so depending on how the question is phrased, it might call for a simplest radical form, so 2 rad 5. Might call for a decimal. I'm not going to worry about that right now, but it would be units, not square units, not cubic units or anything like that. All right, so you got all those little, oh, forgot the bottom. Oh, so say. All right, so let me actually not worry about that right now. All right, because then what I have to do is divide it by, if I want the distance. You know, it's a satisfaction of a job well done, except I didn't finish the job. You know, that a classic me situation. So we're looking at D would be equal to radical 20, and we're dividing off radical 14. So yeah, at this point, it's like, oh, okay, so how are we going to represent this? I mean, we could simplify the top radical. I'm not going to make you rationalize denominators. What I could say instead is that this is going to be the square root of 10/7, and those would be units. All right, so if you want to go decimal form, go decimal form. Again, rationalizing denominators is only a skill. It's not, you know, there's no number that's better than another just because it's rationalized. That's not how it works. Right. So let me shrink this down a little bit so it fits a little nicer. And there it is. All right. So yeah, pick your method and go from there. Yeah, I mean, you could get the answer from GeoGebra. You put in your parametric, you put in your coordinate, and then you just type in distance, and it'll ask you for distance between two objects. So you can get the answer. I'm not concerned with the answer. I'm concerned with you knowing how to do the approach, the process. But when in doubt, if you're really concerned, like oh, I want to come up with the magnitude of the cross product, but I'm not so strong with trig, and I don't like this other method. Find the cross product and find the magnitude of that result. You can't go wrong with that. And it'd take you a little longer, so maybe that's going wrong with that. But you really, in terms of the veracity of the technique, it's perfectly fine. All right, equation for a plane in 3D. Equations in 3D for planes specifically are defined based off of the normal vector, right? Because what happens is as the normal vector goes, the plane goes, right? Because the plane is always orthogonal to the normal vector. So if I know the relationship between two normal vectors, I also know the relationship between the planes themselves. All right. So what we're going to do is come up with the formula, the derivation of the formula, and then we'll talk about the characteristics and attributes of those formulas. So find the equation of the plane given that the points P is xo, yo, zo, and it's perpendicular to the given vector, the normal vector. Right? So normal in that it's perpendicular, just like it meant in Calc 1. You know, you had the tangent line and you had the normal line. Normal was perpendicular to the tangent. Right? Use the fact that the displacement vector between the given point P and an arbitrary point Q, now Q is XYZ, Q equals XYZ. In the plane, it has to be perpendicular to N, which means their dot product must be equal to 0. All right, so let's first tackle the PQ, which is the displacement between X sub O, Y sub O, Z sub O, and XYZ. So X minus X sub O, Y minus Y sub O, Z minus Z sub O. N is just ABC, normal vector, right? So when I'm dotting those two vectors against one another, it's a fairly simple concept. Carrying it out, a little tedious, but we get the job done. A, B, C, dotted against the displacement vector gives you a result of 0. All right? And again, it's 0 because the dot product between two vectors, if it's equal to 0, indicates that those two vectors are orthogonal to one another. Right? So I can multiply. So I'll have AX minus AX sub O plus BX minus BX sub O, BX, geez Louise, BY minus BY sub O plus CZ minus CZ sub O is equal to, not a no, equal to 0, all right? So what we're gonna do, just for clarity, is we're gonna get rid of these guys and just shunt them over to the other side. So we're looking at AX plus BY plus CZ is going to be equal to the same stuff, just with subscripts. All right, so that's what I'm going to do here. I'm going to chuck in a couple of subs. All right, so you'll look at this and say, okay, well, that's dandy. Like, what does that give us? You know, the left side looks an awful lot like a standard form for a linear function. The right-hand side just looks like kind of a standard form for a linear function, just with subscripts. Okay? But what we can do is we could call, you know, create a new variable, call this D, just for brevity, where D is equal to the dot product between the normal vector N and your point P. Okay. Your vector, your point P, sorry, in vector form, so we make it vector P. So that's the little trade-off there. It's point P making up the displacement vector PQ, but if we call it, instead of point P, vector P, then the dot product of that gives us D. All right, so because what's going to end up being the case is on the left-hand side, you're looking at the dot product between N and Q, vector Q. On the right side, it's N and P. That's all you really need in order to come up with the standard form of a plane, right? So let me shrink this down a little bit. And I'll just kind of jot the process here in that little space that I created. Make it red. So what we do is you dot N dotted against Q and set that equal to N dotted against P. That's the equation of a plane. All right. So when I first learned this material and first started teaching this course, very by the book, where it's like, well, that's the formula. You know, it's ax plus by plus cz equals this, any other thing. And the more I thought about it, the more I started coming up with my own ways of doing things, you know, just like any other teacher would, students too, tutors, etc. That's where that magnitude shortcut that I've been talking about came from. Honestly, it came from me just sitting there the other night being like, oh, wait a minute, why don't we just use that? You know, so you're the first class that's getting to use that modified version of it, just because, you know, it was by the book, and now it's like, oh, well, this is a better way, you know. So when I want to write the equation of a plane containing a particular point, and we know it's perpendicular to a vector, then we're kind of ahead of the game here, because we have the vector already. If it's perpendicular, they're flat out telling us the normal vector is n. Well, the normal vector is n. They're telling us the normal vector n is 3, 3, 6. All right. So then the other piece is addressing the concept of the given point. All right. So that given point is point P. So point P corresponds to vector P, which would be 2, 2, 1. All right, if I give you a point in space to create a vector, I find the displacement between that and the 0 vector. So 2 minus 0, 2 minus 0, 1 minus 0 gives us this displacement vector P of 2, 2, 1. All right, now the Q vector, that's the weird one. It's like, oh, well, where's point Q? Well, this is going to be an equation in general terms. So there's going to be an x, y, z built into it. All right, so Q is just, we're going capital Q here. Capital Q corresponds with point, so point Q would be equal to just x, y, z. Vector Q would be vector x, y, z. The displacement between coordinates x, y, z and the 0 vector. So x minus 0, y minus 0, z minus 0. Right? So then if I want to apply my handy dandy shortcut rule, which allows you to pretty much do this concept in your head, n against x. All right, so each of the corresponding values, components between n and q, I said n against x, I meant n against q. We'd be looking at, let me get my drawing tool here. We'd be looking at 3x plus 3y plus 6z. And then when I compute n against vector p, so that's n against p, multiply the corresponding parts and add them up. 3 times 2 is 6. 3 times 2 is 6. 6 times 1 is 6. So we're getting 3x plus 3y plus 6z is equal to 18. Right? So that's the equation of the plane. All right. So that plane is going to pass through, or it's going to contain the point 2, 2, 1. And it's also going to be perpendicular to the vector 3, 3, 6. All right. Now, if I want to sketch the plane, what I do is I find the intercepts. All right. I find the x-intercept, y-intercept, and z-intercept. So x-intercept. So the x-intercept happens when y and z are equal to 0. So that collapses my plane equation down to 3x is equal to 18, making x equal to 6. So what I can do is I could plot 6 points along the x-axis. Then I would compute the y-intercept. which only occurs when x and y are equal to 0, corresponds to, oh, no, I'm sorry, x and z are equal to 0. 3y is equal to 18, which gives us y equals 6. So 6 units along the y-axis. And then finally, the z-intercept occurs when x and y are equal to 0. So z-intercept, x equals 0, x equals y equals 0, which means that 6z is equal to 18, which means z in turn is equal to 3. So at that point, I have intercepts that I can connect. Now, we're not going to get a full look at the plane in its glorious infinite form, but what we can do is get a little cross section of it that exists in that positive x, positive y, positive z octant, all right? Because instead of quadrants, we have 8 different regions that are separated by the x, y, z axes, right? So line segment, line segment, line segment, and then shade that bad boy in. Let me see if I could actually use my shading function. Yeah, there you go. But shade it in a way that makes sense to you. But that would be the first octant cross section of that plane. All right, so it's not too crazy. You know, coming up with the plane itself didn't really take a lot of work. It's just a little computation after that to come up with the x, y, z intercepts. But then that's really it. Right. So number 7 is kind of along the same lines. And in fact, I could say, you know, like let's put a star on that one. So you could try that one on your own, and then we'll come back to that next class. Intersection of the planes. What I was saying before is that planes go where their normal lines go, or at least they behave according to their normal lines. And so if normal lines intersect, then the planes intersect. If the normal lines don't intersect, then the planes don't intersect. All right. So, and if they're skewed, then the planes are going to be skewed to one another. Although skew planes are kind of hard to visualize because those are fourth dimensional happenings or happenstances. All right. So what I'd be looking for here when it says find the equation of the plane containing the point and then also parallel to that given plane is just the idea that if planes are going to be parallel, then their normal vectors have to be parallel, right? So that allows me to take the normal vector here. So n would be equal to 2, 1, 1, just the coefficient of x, y, z. Because again, we're looking at n times dotted against the vector q and n dotted against the vector for p. So, you know, undot it, and the n would be 2, 1, 1. So now I could use that plane, that normal vector to come up with the equation of the plane that involves a point 3, 1, 4. Right. So then this becomes my point P. Right. So vector P, same points or same components, I should say, 3, 1, 4. So then using that information, I could say again, NQ, so 2x plus 1y plus 1z is going to be equal to, and then we dot the n and p against one another. So these two get dotted and added together. Or, well, dotted, which will add them to the products of the corresponding parts together. So 6 plus 1 plus 4 result 11 on the right-hand side. So the equation of the parallel plane would be same left side as the original plane, but the right-hand side would just be 11 instead of 1, right? So that's the displacement between the two, right? But if you need to find intersecting planes, now we got some work to do. All right, the intersection of two planes. Well, we got to find whether or not they're normal vectors intersect one another. Well, let me go back to the process here. All right, to find the line expressed in parametric form. So we're looking, our result should be a line. That is the intersection of two planes. Eliminate one variable from the two equations. Okay, then solve the remaining equation for one of the variables in terms of the other variable. Let the other variable be the independent parameter. Then write down the remaining variables in terms of that independent parameter. So that's a wordy way of expressing a fairly simple idea, which I'm going to talk to you about in a second. But we're going to use a linear algebra approach just to streamline the process. Otherwise, the algebra can get a little out of hand. Although for this example, the algebra is never going to be that bad, no matter which approach you use. But it could be. So we want to use a one size fits all kind of mentality here, if possible. So here's one equation, the equation of a plane: 3x minus 5y plus z would be equal to 4. All right. So what I want to do is, again, find the intersection between these two planes. There's nothing different in terms of the mentality that we're going to use when we're finding the intersection of two equations versus three equations, like we did before with the finding of two lines we're going to intersect with one another. There's really no difference in the mentality. So we're gonna row reduce, and we're going to come up with that solution. It's just a question of what that means. Like once we come up with that solution, all right. So we're going to strip this down into its coefficients. Three, -5, 1, 4. All right. This is what's going to go into our calculator. So let me just clear everything. Start fresh, new matrix. This is a 2x4. So I'm going to expand my number of columns. So 2. Oh, get back in there. 1, 1, 1. 3, -5, 1, and 4. All right. So now we're going to row reduce. So R ref A, and it gives us this glorious mess. All right. So what we want to be doing is looking to see if there's a. Sorry, I just want to expand it a little bit, just so you can see that fraction option there. Yeah, we want to see if there's a little nicer way of representing it, because that was pretty hideous. We don't want those. We don't have to write those decimals down. Slash.
Professor.
Yeah.
Sorry, can you show again on Desmos how you got the matrix format, how you type it to get that?
Sure. Yeah.
The first step.
Yeah, you select new matrix, and then you see at the bottom where it says edit matrix. Yeah, increase the column numbers.
Okay, so, gotcha. Thanks.
Yeah, no problem. Oh, I just undid it. All right, well, I could do it again. RFA brings it up, and now we have, again, that set of fractions rather than the decimals. So we don't want the decimals, all right, because it's going to introduce an unacceptable amount of inaccuracy to our solution. So you got to have it as a fraction if it can be represented as a fraction. A little tip: If a question doesn't give you rounding instructions, then your answer should be a fractional value, right? So just keep that in mind, and good things tend to happen. Or you could avoid terrible things happening. How about that? So 1, 0, 6 13ths, 9 13ths, 0, 1, 1 13th, negative 5 13ths. All right. So we run into the little issue here that maybe you don't recognize yet. The linear algebra people know exactly what I'm talking about, but I want to get the nonlinear algebra people to know what I'm talking about too. Since we know that this follows the format of coefficient x, coefficient y, coefficient z, and then constant, we're looking at 2x plus 0y plus 6 13ths z is equal to 9 13ths. Right, and then 0x. Oh, I put a 2 for some reason. I don't even know why. I know why. I was looking at the 2, but shouldn't have been. Should have been looking at the matrix that we just created. All right, so 0x plus 1y plus 1 13th z is equal to negative 5 13ths. All right, so I'm done with this for now. Just kind of shunt it over there. I want to clean this up. I want to make it x plus 6 13ths z is equal to 9 13ths. And then y plus 1 13th z is equal to negative 5 13ths. All right. Not the final answer, but we're getting there, because when we have parametrics, we need to have x, y, and z solved in terms of t, linear equations in terms of t, if I'm looking for a line. So that's not even remotely what we have, but it will be in a second. So what I'm going to now do is solve each of these for x, the independent variable, dependent variable x and y specifically. X equals 9 13ths minus 6 13ths z. Y is equal to negative 5 13ths minus 1 13th z. All right, the issue is I don't have z equal to anything. All right, but it has to be equal to something if these two planes intersect with one another. Fun fact, I'm not going to tell you that a plane, I'm not going to tell you to find the intersection if there is no intersection. Right? I know sometimes, there's like wiggle room with questioning and how it's structured, but this is the kind of thing I don't like to mess around with, because it's a lot of work to find out that there's no solution. It'll say find the intersection if it exists, in which case you kind of know going in that that's on the table. But if it says find the intersection, there's going to be an intersection, right? So what we do, how we handle this, is to say that z is what we call a free variable. All right, it's a free variable, meaning it could be anything, all right? Because z is unaccounted for, but that essentially means that x is equal to this, y is equal to that for all values of z, right? Or for any value of z. So what I could do is I could let z equal whatever I want. So I'm going to say let, and just to kind of keep it simple, I'm going to let z equal t, some parameter t, right? And so what I get as a result is the plane, the line. So I'll call it line L, 9 13ths minus 6 13ths t, comma, negative 5 13ths minus 1 13th t, comma, t. All right, so again, the x, the y, and the z. All right. Now, like I said, I could have let z be whatever I want. I chose to let it be equal to t. But if you think about it, maybe the better choice is to let it be equal to 13t, because then it'll cancel out the denominator for the 6/13ths and the 1/13ths, give you a little cleaner expression. But that's your choice, right? As long as your line L is equivalent to my line L, then you're fine, all right? Because remember, we're talking about parallel vectors here, right? So if I'm dealing with, I got negative 6/13ths, negative 1/13th, and 1 as my parallel vector. If you got negative 6, negative 1, and 13 as your parallel vector, they still have the same root vector to them, right? So they're going to be parallel to one another, and that gets the job done, right? Because a vector that's parallel to another one would still fall on the same line, right? So it's up to you how you want to handle that, but that, you know, I like to just keep z as simple as possible. Let z equal t, and then there you go. All right. Now there is another something to consider anyway. Let's say you went through this whole process and you were only you canceled out. Let's say, well, not canceled out, but you were able to solve for x and z in terms of y. Then y would be your free variable, and you would let y equal t and then build it off from there. So it doesn't necessarily have to be the case that z is going to be equal to your parameter t. Any of the variables could be your parameter t depending on how you work it out. All right. Distance between point and a plane. I'm actually going to toss this topic. Only because we're going to pick it up later when we get to differential, not differential equations. Wrong course. Lagrange multipliers. It's a part of differentiating several functions of several variables. So I'm going to toss this for the sake of time and energy and all that stuff. So bloop and bloop. Might come back to it later on in the course if we have time, but I don't anticipate that happening. I also may make it part of another assignment. We'll see. Because now I feel the need to make my X look like a quality X here. The little things I get obsessed with. Whatever. All right. So we're going to hop on over to vector valued functions. And actually, let me stop this recording.